just doing vivid. It's just SUT.
Yeah, so if you're just using the then it's just
Only SUT. And then SUT carries down here too. SUT, SUT. There's gonna be a difference. I didn't know.
Yeah, but if you have n number of cycles.
N number of cycles.
Is that what you're supposed to? So
Now, what is it? Little n is factor safe. Big N is totally different calculations. Which we have different calculations. That's a good network. And this one is this is first and second.
Yeah.
This is third.
correct.
The third is the one that we will utilize to then find n. Because we need reversible to have this sigma in. So we're gonna find this. But then we're gonna find this.
So we can use that factor safety as well. Why can't we use factor safety?
Because this factor safety is different than factor safety. Because this is a non-reversible system, that's a reversible system. So this is a completely reversible system.
And for whether to be slightly the same right here. Yeah, because it's not.
That's what I'm saying.
Yeah.
We said different. Other than just like reversible, completely reversible and general. Well, we know it's reversible or not based off the signal values we get. But what if it was doing? Well, with the 0 to 16. Yeah. Well, you'll see if you're given like -16, +16, you get layer type 3. In the back horizontal signs. And the mean is 0. Now, if you're given like 0 to like 32, if you're given 2 totally random things, you type 1.
If it's reversible, we can reduce that. But if it's reversible, sigma is you can't define sigma means 0.
Right.
Sigma rep is if it's reversible. It's not reversible. Then it would be that's what it's doing. Because if you look at both of your equations, one of them is divided by sigma, and if it's a reversible, it can't be.
Hey guys, how's it going?
What? Yeah. What happened?
Metropolitan Water District?
Unfortunately.
Oh, shit. I got a Toyota internship. Oh, shoot. Nice. What? Yeah. I can see you. I think I have like a muscle jack. You don't like it. Yeah. All right. It's kind of weird Yeah, it's actually better. Originally I was assigned to but my mom, like grandma was there. And technically, but it's like, so it's a little bit closer. It's not really as bad. Plus area is better. It's right next to me. But yeah, it's all very. It's a lot better. Right, so
It's gotta be. That's good. Congrats. Sweet. Here's that.
Is it gonna go here?
It's kind of, it's not, it's a real small company, so I think it's taking a long time. So, but I'll do nothing. Or I'll do like, yeah, full time in summer and part time in studios. Should be till I graduate. Open it.
I guess we like them.
I'm not they all take that off my job. I think they all, I think he offers like pretty much. I don't know how you. Probably had briefly about this. I mean, it's interesting. It's not, it's a lot of electrical work, which is like, I mean, I don't know anything, but what I'm interested in.
He's just separate.
So it's all project based. I was throwing it on project with another. Yeah, it's all project based, but I mean, by the time Greg graduates, he might have another job.
Oh, yeah.
So maybe it won't go outside.
They know they have controls, right? You have testing.
I mean, kind of.
You guys touch with the controls.
Yeah, there's a lot of controls, like they're building, or they're gonna start building like two massive control panels that will power the whole line for. But it's weird because they're moving. This company, I don't know, it's kind of weird. But it's so far, it's
Yeah, just so you don't like do any designing it.
no, it's one, I mean, not professionally, but it's one of those things like I know how to.
Software wise. Yeah.
All right, it's 2:30, so let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, doing good. All right. So remember our midterm is next Monday. Okay, so that's going to be 4/25. So today I posted a study guide. I posted a review poll. So just like last time. And so, because our midterm is going to be on Monday, I'm going to film the review video on Wednesday. So if you could fill out the poll before Wednesday morning, you can make sure your voice is heard for that. Okay. And so the topics for this midterm are going to be all convection, basically. So when we first started with convection up until maybe about the first 15 minutes today. So that's what's going to be on the midterm. Okay. We are going to start something new, and so we're going to start radiation today. But the radiation stuff is not going to be on the midterm. Okay, so you're only going to be responsible for the convection stuff. All right. So besides that, we have one more homework that's due, and so homework 6 is due on Wednesday. All right. So make sure you guys are doing that. I have gotten quite a few questions specifically about problem 2. So I will say this. So problem 2. If you want to get my exact numbers for all of the parts. You would have to evaluate the fluid properties at the temperatures that I emailed out last week. But with that said, even with that, if you're depending on what calculator that you're using, you might get different numbers, and that's okay. So I've been telling people that for that problem, what I'm looking at is your process more so than the numbers. Okay. And let me say this for the exam too. So a big part of this unit has been looking up fluid properties on lines and things like that. For the midterm exam, you're obviously not going to have your textbook or your computer with you. And so I'm going to give you the fluid properties. And so you're not going to have to worry about that. Okay. And so I think that should standardize everything too. So everyone should hopefully get the same solutions for everything, because everyone's going to be using the same properties. Okay. But all the NUSO correlations, I would definitely write those down on your cheat sheets. Okay. And so same format as last time. So you can have a single cheat sheet for 8.5 by 11, both sides. You can write whatever you want. Okay. All right. And so that's it for my announcements. So are there any questions I can answer before we get started? Okay. All right. So let's go ahead and get going. And so we have just a little bit left to finish up with heat exchangers. Okay. Specifically, I want to do an example that has to do with effectiveness of heat exchangers. And in fact, the homework problem has to do with effectiveness. So actually, a few of the questions I got over the weekend have to do with, how do we use this effectiveness and how can we compute heat transfer rate if we don't know the output temperatures? Well, you can do that if you know the effectiveness. Okay? And so just very briefly, effectiveness is basically a way for us to assess how good your heat exchanger is, because there are good heat exchangers out there, there are bad ones, right? And we usually give this symbol epsilon. Okay. And what this epsilon represents is basically a ratio. Okay. And so the ratio that epsilon represents, it's basically a ratio that's between 0 and 1. And so on the denominator here, we have the maximum possible heat transfer. Okay. And on top, what we have is the actual heat transfer. Okay. And so there's no such thing as a perfect heat exchanger. Well, theoretically, you can achieve it. But practically speaking, you're never going to design a perfect one. And so every heat exchanger can basically be rated, based on how much it's or how well it's performing compared to the theoretical maximum. Okay. And the way that we compute epsilon depends on the geometry of the heat exchanger. Okay. And so there's all different kinds of formulas for epsilon out there. But for our class, we're basically sticking to the simplest types of heat exchangers. And so we have two. And so we have one for counterflow heat exchangers, and we have one for parallel flow. Okay. And so let me go over parallel flow first. Okay, because that's the one we're going to use in the example. And so epsilon for parallel flow is be 1 minus exponential of minus NTU times 1 plus CR, all divided by 1 plus CR. Okay. Where NTU and CR, those are quantities that you compute based on the resistances and the mass flow rates and everything. So we'll go over that in the example soon. Okay. And the expression for counterflow effectiveness, which you use for the homework, is given by the following. So we have 1 minus exponential times minus NTU times 1 minus CR, all divided by 1 minus CR exponential times 1 minus NTU times 1 minus CR. Okay. Right. And so you can use these expressions to basically state, even before you do any kind of heat transfer calculations, how good this heat exchanger is going to be. Okay. And this works great because, a lot of times you'll be given situations, just like the homework problem, where you're asked to analyze a heat exchanger with only knowledge of the inlet temperatures. Okay. Okay. Because before, the example I think we did last week, we had knowledge of both the inlet and the outlet temperatures. And so if you have inlet and outlet temperatures, that's great. And so you can make a lot of statements based on how much heat transfer is going to occur. But a lot of times, especially in practice, if you're designing a heat exchanger for a device, a lot of times you don't know right away what the outlet temperature is going to be. And so you're going to have to come up with a different way to analyze your heat exchanger, and effectiveness is one way to do that. Okay. And so this example here, I think should be helpful, for those of you who are still working on problem 2 of the homework. This example should kind of show you how you're supposed to approach these kinds of problems. Okay. All right, any questions on this before we jump into the example? Okay. All right, so let's see. So for this example, we have a parallel flow heat exchanger. Okay. And this one's unique because we're going to have water. We're going to have water in both parts of the heat exchanger. So the only difference is that one of them is going to be hot water, the other one's going to be cold water. So here's our concentric tube heat exchanger. Okay. Up top here, we have water, which will be the cold fluid. Okay. And in the middle, we're going to have water also, but it's going to be hot. Okay. And we say that they're running in parallel flow. So both flows are going in the same direction. Okay. And so in this situation, we're only going to know the inlet temperatures. Okay. And so for the hot water, 31 years old, my voice still cracks. All right, so for the hot water, our inlet temperature is 50 degrees C. And it's coming in with a volumetric flow rate of 15 liters per minute. And so that's going to be, that's our volumetric flow rate. Okay. And so our cold water is going to be coming in at 20 degrees C. And the flow rate for this one, where is it, is 20 liters per minute. And so, of course, for these volumetric flow rates, QH and QC, we're eventually going to use these to compute the mean velocity. Okay, but they're not mass flow rates, and so we'll see how those are used. Okay, so let's look at geometrical parameters. And so the inner pipe has a diameter of 2 centimeters. Okay, so that's DI. The outer pipe, which is the pipe around the whole thing, this will have a diameter of 5 centimeters. So this is DO. Okay. But in addition to this, we're going to say that the inner pipe has a wall thickness. Okay? So this is another thing that's been kind of throwing people off a little bit for the homework problem. And so, these flows are not separated by, a paper thin sheet. They're actually separated by some material in between. Okay? And so we say that the thickness of this solid is going to be 1 millimeter. Okay? So we're going to have 1 millimeter on each side, basically. Okay. And so from this problem, we're interested in computing. One, we're first going to compute the effectiveness. Two, we're going to compute the total heat transfer rate. And three, once we have the total heat transfer rate, we can compute the outlet temperatures for both fluids. Okay. And so here we have a heat exchanger problem, but we're going to have to take a different approach than what we did before because we only know the inlet temperatures. Okay? And so to compute things like the heat transfer rates or the outlet temperatures, we're going to need to compute the effectiveness first. Okay. And so this example is kind of nice because it kind of lays out the process for you in order for you to do that. Okay. Any questions on the setup for this example? Okay. All right. So let's go ahead and get started. And so first thing, we have the effectiveness. And so since we know this is a parallel flow heat exchanger, and so we're simply going to use this formula up here. Okay. And so the effectiveness for this heat exchanger is going to be 1 minus exponential of minus NTU, 1 plus CR, all divided by 1 plus CR. Okay. And so, of course, what we need to compute this is both the NTU and the CR, right? And so NTU is a function of the total resistance, okay? And so NTU is given by 1 divided by m dot Cp, okay? So you have the product of the mass flow rate multiplied by the thermal capacity. Okay. We're going to take the minimum because we have two fluids, and so we're going to take just simply the minimum between those two quantities. Multiplied by the total resistance, and so total resistance, we're talking about thermal resistance here. And so in order to compute this, we're going to need to compute the convection coefficients, okay? And then CR is just a ratio of the two m dot CPs, okay? So we have an m dot CP, we have one that's smaller, and we have an m dot CP that's bigger, okay? All right, so we have, you know, a relatively simple expression here for the effectiveness, but there's a lot of work that goes into computing it, okay? Principally, you know, we have to compute the total thermal resistance. And so, you know, just based on that, we're going to have to compute the convection coefficients, okay? And so let's work on that one first. Okay. Because if we took, you know, if we took the situation, and so just intuitively speaking, right, we know that heat is going to transfer from the hot water to the cold one, right? And so no, heat's going to go from the inner pipe to the outer one, right? And so if we draw the thermal circuit for this problem, okay, the thermal circuit would look like this. And so we have three different resistances, right? And so one here will be the hot end, and the other end will be a cold end. And so first of all, we have the convection resistance of the interflow. Okay. And so you have 1 divided by HI times AI, right? But that's HI is the convection coefficient for the inner fluid, and AI is the inner surface area. Okay. Then we have the conduction resistance going through the wall. And so the conduction resistance is going to be ln of di plus 2t divided by di multiplied by 2 pi kl. The way I got to di plus 2t is the fact that, you know, if you look at the inner cylinder here, if I kind of draw it out, it might be easier to see it like this. Okay. Right, we know the inner cylinder, the diameter for this is di. Okay. But we also know that on the outside of this, we have a wall thickness of T, okay? Because that's the thickness of the wall. And so if we were to measure kind of the total diameter of both together, okay, we apply that thickness twice because we have the thickness on one side of the circle and the thickness on the other side. So that's why I have di plus 2t as kind of like the outer diameter of the solid wall. Okay. Yeah.
Isn't the ratio flipped for the natural wall? That's the outer diameter over the inner?
It is. This is the outer diameter.
Yeah.
Yeah. Because you have just whichever one is bigger on top. Because if you have ln of something that's less than 1, you end up with a negative number. So do is the outer diameter of the entire pipe right here. Right. So this conduction resistance is just in between these two. So it's very, very small. And so, you know, it's just the fact that, you know, when you go from liquid to liquid, you pass through that little bit of solid pipe there. And so that conduction resistance for that solid pipe. Okay. And finally, what we have for the last resistance is 1 divided by HO AO. Okay. Okay. And of course, you know, it would be great to have the conduction resistance or conduction thermal capacity, excuse me, thermal conductivity of the pipe. Okay. And so this K, where did I write it? K is what? This is for the K for copper. And so I don't think I wrote it down in the problem, but I think I looked it up in the table. Okay. Because in the problem it was I said it was a copper heat exchanger. Okay. And so I don't believe I have the value here, not after I read the example. But that's something you can look up in a table. Okay. And the length of the heat exchanger, which is the length in this direction right here. Okay. That length is 1.5 meters. Okay. And so with that in mind, the only things that we don't know right now are the 2 convection coefficients, okay? Which makes sense because, you know, we are in the convection unit. And so let's go ahead and run through the process to compute those convection resistances or convection coefficients. Okay. All right, and so we have two flows here. And so we have a flow in an inner pipe. And so that's simply internal convection in a tube. And we have flow in the outer annulus as well. Okay, so just like any kind of heat exchanger. And so first thing we're going to do is we're going to compute the properties of water. Okay. Normally, you would do this for the two fluids separately, right? So you'd get a set of properties for the inner fluid, a set of properties for the outer fluid. But since both of these are water, I'm just going to do one evaluation. Okay, and I'm going to do it at the average between those two temperatures. And so we're going to assume that the film temperature is 35 degrees C. Okay. And so at 35 degrees C, we have a CP of 4,200 joules per kilogram K. Okay. We have a density of, bless you, 1,000 kilograms per meter cubed. We have a kinematic viscosity of 1 times 10 to the 6, 10 to the minus 6 meters squared per second. We have a thermal conductivity of 0.6 watts per meter Kelvin. Okay. And so first thing we're going to do is that based off the density, we're going to compute the mass flow rates. Okay. Because we weren't given mass flow rates in the problem, we were given volumetric flow rates. Okay. And so to compute mass flow rates, what you have to do is you have to take the density and you multiply it by the volumetric flow rate. Okay. And so we're going to take density times QI, okay, QI being the hot fluid. And so if you do that, and you do all the conversions, of course, because the volumetric flow rates are given to you in liters per minute, what you get from this is 0.25 kilograms per second. And for the outer fluid, you do the same thing, and you get 0.3 kilograms per second. Okay. Okay. And so we'll use that later, but the density was right there for us. And so you might as well just compute that. Okay? But let's go ahead and continue on in computing the convection coefficients. Okay? Right, and so after we compute the fluid properties, the next step, of course, is to compute the Reynolds numbers. And so let's do it for the inner fluid first. Okay, so this is for the hot water. And so we have UM times DI, all divided by nu. Okay, where UM for the inner fluid is going to be the volumetric flow rate divided by the cross-sectional area. Okay. And so we compute that, we get a Reynolds number of 15,915.5. Okay. Okay. And of course, since this is greater than 2,300, we know that this is turbulent. Okay, so let's do the same thing for the outer fluid. Right, so outer fluid is our flow in an annulus, right? And so we have our mean velocity multiplied by the hydraulic diameter, right? Remember, whenever we're considering flows in an annulus, instead of multiplying by the diameter, we do the hydraulic one, okay? Where the hydraulic diameter, DH, this is the outer diameter of the entire heat exchanger, DO. And from this, we're going to subtract out the inner diameter. Okay? But it's not just going to be DI, it's going to be DI plus 2T. Because remember, we have that thickness of pipe that's separating the inner fluid and the outer one. And so the amount of area that's actually being used to, for the outer fluid is DO minus DI plus 2T. Okay. And the UM here, UM is going to be QO dot divided by AC, okay, where AC is going to be pi over 4 times DO squared minus, again, we have DI plus 2T squared. Okay. Because remember, after you get past DI, we actually have solid pipe there. So there's going to be no flow inside that solid pipe. And so when you're computing things for the outer fluid, you have to subtract out that thickness. Okay. Okay, and so we do all these computations and we plug in the material properties. And we get 5,835.68. Okay. We see this is greater than 2,300, and so this is also turbulent. Okay. And so since we have both flows are turbulent, we're going to use the Nussel number correlation for turbulent flow. All right. Any questions on this? Okay. Okay. And so the Nussel correlations for turbulent internal flow, what we have is, and U is equal to 0.023 times the Reynolds number to the 4/5 multiplied by Prandtl number to the N. Okay. Where N, remember, is either 0.3 or 0.4, depending on if the fluid is being heated or cooled. All right, and then once we have the Nussel number, we can then compute the convection coefficient multiplied by the, this is multiplied by, excuse me, so this is the convection coefficient multiplied by the diameter divided by the thermal conductivity. Okay. All right, so using that, let's compute for the interflow. So interflow is going to be KF divided by DI multiplied by 0.023, Reynolds number to the 4/5 times Prandtl number. Okay. Since the inner fluid is being cooled, right? So the inner fluid has the hot water, and so it's going to lose heat to the other stream. Okay. We're going to use a Prandtl coefficient of 0.3. Okay. We plug in all the numbers for this, we get a convection coefficient of 3,250 watts per meter squared Kelvin. Okay. Okay. Then we have an HO. HO, we have the thermal conductivity of the water. Then we have the hydraulic diameter, DH. Again, 0.023, Reynolds number to the 4/5. Okay. Since the outer fluid is being heated, we're going to use a Prandtl number to the 0.4 power. Okay. And so we plug in all the numbers for that, we get 870 watts per meter square Kelvin. Okay, so those are our two convection coefficients. And so now that we have our convection coefficients, we can use that to compute our total resistance. Okay. And so if we compute our total, we get our total is equal to. Okay, so I'm just gonna plug into this formula up here, right? And so we're gonna add up all these resistances here. And so we add all those up and we get 0.1435. Okay. And there's units for that, but I always forget the units for thermal resistance. So, we'll just leave it as a number, okay? Okay. And so now that we have the total resistance, we can use that to compute NTU and CR, right? Because remember, with these convection problems, there's so many steps involved, right? And so remember, we originally set out on this problem with the goal of computing the convections, right? And so we basically want to plug into this expression here, but in order to do that, we have to compute NTU and CR, okay? Okay, but to do that, we have to compute what the m dot CPs are, right? So we're going to take the m dot CP of the inner fluid, okay? We take the m dot CP of the outer fluid, okay? And so to compute these, you just take the product of the mass flow rate and multiply it by the thermal capacity, okay? And so for the inner fluid, we found earlier, the mass flow rate is 0.25 kilograms per second. Okay. And we know that CP for this problem, we looked it up, is 4,200 joules per kilogram K. And so we plug those in. We use our calculator. We get 1,050 watts per Kelvin. Okay, and we do that for the outer fluid. So for the outer fluid, we have a mass flow rate of 0.33, not 35, excuse me. Okay, 0.33 times 4,200. And so once we do this, we get 1386 watts per Kelvin. Okay. All right. And so just based off these numerical values, we can see which one's the minimum, which one's the maximum, right? As we can see this top one here, this is our minimum. Okay. And this bottom one, since it's higher, this is m dot CP max right here. Okay. And so when a problem asks you to compute the m dot CP min, m dot CP max, right? You're going to have to compute m dot CP for both flows. And then just see which one's bigger than the other one. Okay. So now that all of that's done, we kind of just have a cascade of just kind of plugging and chugging. Okay. So first, let's compute NTU. Okay. So NTU here is 1 divided by m dot CP min multiplied by our total. And so we do this, we get 0.0665. Okay. Okay. So that's our NTU. Our CR is just the ratio of these two. So CR is going to be 1,050 divided by 1386. Okay. And so that's going to be 0.758. Okay. So now that we know NTU, now that we know CR, we can plug this back into our expression for effectiveness. Okay. And so I'm not going to repeat that entire expression right there, but you should get an effectiveness of 0.062. Okay. And so this heat exchanger, and so what this tells us is that this heat exchanger, as is currently constructed with the length and diameters as they are, only achieves about 6.2% of the maximum theoretical heat transfer. Okay. And so that seems really bad, right? And so, we went through all this trouble just to only get 6% of the value. But remember, that maximum theoretical heat transfer, that's more of a pipe dream more than anything, right? And so you can only really achieve that if you have a heat exchanger that's infinitely long, okay? And so you can see this heat exchanger is pretty long already. And so it's already 1.5 meters, which is, all things considered is pretty long for one of these devices. And so even with that, you only get 6.2%, okay? And so and so when you're computing these effectivenesses, don't expect things to be in like the 50, 60, 70%, okay? That's not how you should think about this effectiveness. And so, something around this range, and even, if you can get like above 0.1, that's usually a pretty good heat exchanger, And of course, it's application dependent, but, something like that's usually, you're doing pretty good. Okay, any questions on this part right here? Yep.
Could you scroll back up to the equation?
Yes.
Why did you use 0.4?
Yeah, so we use 0.3 and 0.4 depending on if the fluid's being heated or cooled. And so for the outer fluid, that fluid's being heated up, right? Because we have cold water running on the outside and hot water running on the inside. And so you use 0.4 if your fluid is being heated up, and 0.3 if the fluid is being cooled down. Mhm. Okay, and so that's the first part of this problem. Okay. Next, we're going to compute the total heat transfer rate. All right, and so to compute Q, and so I think this is probably one of the bigger questions I got on the homework, right? And so normally when you compute Q, you take the product of m dot Cp, and then you take the difference of the inlet and the outlet temperatures, okay, for the same fluid, right? And so if you know the inlet and outlet temperatures of the fluid, you take the m dot Cp, the mass flow rate times the thermal capacity of that fluid, you multiply by that, and that gives you Q, right? Of course, for this problem, we can't do this, right? Because we don't have the outlet temperatures. At least not yet. And so what we can do instead is we can say that we can leverage our definition for epsilon, right? And so remember, the definition for epsilon is it's a ratio of the actual amount of heat transfer from this situation divided by the theoretical maximum. Okay. And so if we multiply both sides of this equation by the theoretical max, okay, and we define this actual heat transfer, so we'll just call this Q, because actual heat transfer is way too much to write, okay? We can say that Q is equal to the effectiveness multiplied by the theoretical max, okay? And how do we get theoretical max? Well, the theoretical max is given by m dot Cp min multiplied by the difference in the inlet temperatures. Okay. Because those we do have. And so we have the inlet temperature of the hot fluid and the inlet temperature of the cold fluid, right? And so if you remember from last Wednesday, the theoretical best case scenario for a heat exchanger is that the hot fluid cools all the way down to match the cold fluid, and the cold fluid heats up all the way up until the hot fluid, okay? That only happens if your heat exchanger is infinitely long, okay? But if that's the case, then that's the amount of heat transfer that you have, okay? All right, and so we have everything here. And so if we take epsilon we just computed is 0.062. Okay. M dot Cp min in this problem is 1050 watts per Kelvin. Okay. The inlet temperature is 50 for the hot fluid, and the inlet temperature is 20 for the cold fluid. Okay. And so if we say that our actual heat transfer is only 6% of this, then our actual heat transfer is 1,970 watts. Okay. All right. And so that's how you compute the amount of heat transfer that gets moved in a heat exchanger without the outlet temperatures. All right, any questions on this part here? Okay. All right, and then finally, once we have Q, we can actually use this to compute the outlet temperatures. And so I just crossed this out, but we can actually use this one now. Okay. And so we use the fact that Q is equal to m dot Cp multiplied by Ti minus To. Okay. And this applies for both fluids. It applies for both the hot fluid and the cold one. Okay. Now that we know Q, right, we can go ahead and plug Q in for that. We can then use this to solve for To. Okay. Okay, so let's go ahead and do that. Okay, so first let's do the hot fluid. Okay. So the hot fluid is on the inside. And so if we solve for TO, we get THO is equal to THI minus Q divided by m dot Cp. Okay. M dot Cp of the hot fluid. Okay. And so we get an outlet temperature for the hot fluid to be 48.1 degrees C. Right. We do the exact same thing for the cold fluid, and then we end up with an outlet temperature of 21.4 degrees C. Okay. All right. And so it looks like our fluid temperatures are barely changing, right? And so our hot fluid started at 50 degrees C, and it only cooled down about 2 degrees Celsius, down to 48. Meanwhile, our cold fluid started at 20 degrees C, and we only heated up about 1.5 degrees Celsius. Okay. And so it looks like, we barely did anything. But remember, our effectiveness is only 6%. Okay. And so if we were to make this heat exchanger longer, or if we were to, increase the flow rates, we'd be able to get more heat transfer in these situations. Okay. All right, questions. So the question from the chat is, from this problem, we use the average temperature between the two inlets to get TF and find the properties of water at TF. Can we use the same method for problem 2 in the homework? You could do that, and I think that's probably some of the logic I did to get to temperatures. But with this problem, the difference in temperatures between the fluids was not that big. So we had 50 and 20. I believe for the homework, it's like 120 and 20. And so that's a lot bigger of a difference there. And so if you have such a big difference like that, I would be a little bit hesitant to take just the average between them. But if you have two fluids that are already pretty close in temperature, I would say that's you can go ahead and do that. And so it depends on how big the range is. And so if it's 30 degrees C difference, then I would say go for it. But if it's anything more than like 50, I would say that I would do each one individually. All right, any other questions on this example before we move on to radiation? Okay, all right, and so that's it for convection. And so, let me go ahead and draw a line right here. Okay. And so past this line, so anything past this line will not be on the midterm. But you can expect it on the final, and so don't turn your brain off, and so keep paying attention But just keep in mind that, our midterm is only going to be for convection. Okay, and so with that, we're going to start a whole new unit here. It's about radiation. And so first, let's introduce what radiation is. Okay. All right. And so at this point in the class, we've done a lot of heat transfer. So we've done, 12 plus, 12 weeks plus 45 minutes of, a bunch of heat transfer. And we focus pretty much exclusively on conduction and convection. Okay? Conduction and convection, of course, they're different. But, you could say that they're pretty closely related because, you can think of conduction as heat transfer in a stationary medium, whereas convection is heat transfer that goes into a flowing medium. Okay. Radiation is kind of like the odd member of the family. Okay? So radiation is very different from the other two. Okay. And so let me start by saying this. Okay, so conduction and convection. Okay. Conduction and convection both require what's called a material medium in order to occur. Okay. Okay. In other words, there needs to be some matter that's present in order for conduction or convection to take place. Okay. And the reason for that is that both of these modes of heat transfer, they rely on molecular transfer of energy. Okay. Okay. Even though their exact physics are different on kind of a macro scale, on a micro scale, what's happening for conduction and convection is that, one molecule is gaining energy because it's getting heat, and then it's taking that heat and passing it to the neighboring molecule, okay, which then passes to the neighboring molecule from there. Okay, and so both are kind of like that. And so that's great. And so, most of the heat transfer that we consider on Earth, we can sum it up as conduction and convection because we have material mediums in most places. But it's still possible to transfer energy without material in between. And in fact, a lot more so that we live here in Southern California, we see a great example of this every single day, right? You go outside, you open the window, right? You have the heat from the sun, right? So the sun, it's radiating a bunch of heat, and the only way for that heat to reach the Earth is through radiation, right? Because if you think about what's in between the Earth and the sun, right? We have the moon that's there sometimes. There's like a Tesla floating around there randomly, right? But mostly there's no material in between the Earth and the sun. Okay, and so the only way for the sun's rays, the sun's heat to reach us is through radiation. Okay? What's up? Yeah. I don't think it's being charged all that much. I think it's just floating around in space. And so when we're talking about radiation, it's really important to talk about, what's the physical mechanism that makes it work. Okay? Okay, and so radiation, the way that we're going to define this is the transfer of heat through electromagnetic waves. And electromagnetic waves don't need a medium. Okay? So what's an electromagnetic wave? Well, I mean, light is an electromagnetic wave. Okay? And so if you think of the electromagnetic spectrum, so you probably have heard of things like microwave, ultraviolet, infrared, things like that. So that's what we're talking about. We're talking about electromagnetic waves. Okay? So did you guys learn any kind of like optics, basics of optics in your physics classes, before? Okay, so it's okay. And so, we'll kind of treat it as if, this is everyone's first foray into optics. Because in order to understand radiation, you have to understand, optics to some degree. Okay. Okay, and so that's kind of the reason we save this for last, because it's the mathematics and kind of the physics that are involved with radiation are very different than conduction convection. We'll still see kind of the same concepts, and we'll still see thermal resistances. We'll still see thermal circuits. The way that we're going to compute those is going to be a lot different here. Mostly just because the physics are quite different. Okay, so let's dive into radiation a bit more. Okay, and so I think the next question we can ask is, what emits radiation, or what causes it to happen? And so it turns out that there's really no special requirements to have radiation. The only requirement that you have to have is that you have to be an object, and you have to have non-zero temperature. Okay. And so you have an object here. Here I have an arbitrary potato. Okay. And so let's say that this potato is the temperature Ts. Okay. And so just by nature of being made of stuff and having a temperature, it's going to radiate heat. Okay. And it's going to radiate heat in all directions. Okay. And so you might be asking, do you mean anything? Yes, I mean anything. And so, that roll of toilet paper is radiating heat. Okay. The projector is radiating heat. You are radiating heat. I'm radiating heat. We're all radiating heat. Okay. We're Oprah today. Okay. Heat is radiating heat. That's right. That's right. Okay. And so how do we quantify this? And so the way that we can quantify it is through computing the emissive power. Okay. Okay. You're killing my flow, iPad. Okay. And so the emissive power, we define it as big E, okay, where big E has the same units as heat flux. And so this has units of watts per meter square. Okay. It's defined as epsilon. They're not the same epsilon that we talked about. So it's an unfortunate thing of switching between units, multiplied by sigma, which I'll define in a second as well. My iPad will cooperate. Okay. Times Ts, the surface temperature, raised to the 4th power. Okay. I see there's a question in the chat. What's that? 0 temp meaning absolute zero. That's correct. Yeah. So 0 temp meaning 0 degrees Kelvin. And so, literally every object is radiating heat to some degree. Yeah. Mm-hmm. Okay, so let's go ahead and define all the terms in this expression. And so this E right here, this E of course is emissive power. And so we just define that. This epsilon here, this is known as the emissivity, which we'll dive into more in just a second. Okay. This sigma right here is a special constant. So this is called the Stefan Boltzmann constant. And we can give it its value, and so its value is 5.67 times 10 to the minus 8 watts per meter square Kelvin. Okay. And so the TS, this TS, of course, is the surface temperature. Okay. And this is really important right here. And so when you're talking about radiation, the reference to absolute zero is actually a good one, because here we actually see temperature that's not linear, right? So we have temperature that's raised to the fourth power. And so before, for almost everything else before this in the class, it didn't really matter whether you use Celsius, degrees Celsius, or Kelvin, right? You end up with the same answer. But here, when we're doing radiation, because we have temperature raised to the fourth power, it does matter. And so when you're computing radiation, your temperature should always be in Kelvin. Okay? Okay. And so keep that in mind. And so, for all intents and purposes, from here on out, just kind of use Kelvin for, for everything. Okay, so, all that's fairly straightforward, except for the emissivity. Okay, so let me go ahead and define that. Right, so this epsilon here is not effectiveness. We're not talking about heat exchangers anymore. And so what the emissivity defines is it defines how effective or how well a certain surface can give off radiation. Okay. Because in fact, how much radiation an object gives off is a function of more than just the temperature. Right? The surface properties of the material also have an influence. Okay? And so emissivity is a coefficient, and so it doesn't have any units, and it also varies between 0 and 1. Okay, and so it's similar to the effectiveness in that it defines a ratio. Except now how we determine the ratio is a bit different. Okay. And so of course, these extremes are very, very difficult to obtain. I want to say that they're impossible, but I don't want to comment on it. Okay, because there might be something that approaches it. Okay? And so if you have an emissivity of 0, basically this means you give off no radiation. Meanwhile, an emissivity of 1 means the opposite, which is perfect emissivity or perfect radiation. So that's the maximum radiation. Okay. And so what the emissivity represents is kind of something about like the surface qualities, right? And so think of two very different types of surfaces. So one, let's think of a mirror, okay? And then let's also think of sandpaper, right? And so, those two objects, of course, they're very different. But I think the thing that differs the most is, how smooth those surfaces are, right? So you think of a mirror, you think of something that's really, really smooth, right? And so a mirror would probably be a good example of something that has, something on the higher end of emissivity, just because it's really, really smooth. Meanwhile, something like sandpaper is, very, very rough and coarse, right? Something like that is probably going to diffuse, a lot of the optical rays that hit it. And so that's going to have a lower emissivity. Okay? And so depending on the surface qualities, you're going to have higher emissivities or lower. And this is usually a property that you can look up in a table. But sometimes it's not as not that useful. Yeah.
So so you said that maximum radiation is hard to reach.
Yeah.
So like when a radioactive material indicates that exposed more radiation does not have the capability to reach one, but has the capability to closely reach one.
So there's a few things at play. So the emissivity is just a function of just how the surface is and how well that gives off light, basically. And so, but on top of that, you also have the surface temperature as well, right? So they both affect how much radiation you can give off. And something like a radioactive material, I mean, there's a lot of other stuff going on with radioactive materials, but then, something like that probably has a much higher surface temperature, and their emissivity, could be something else. Yeah. Right. And so in fact, emissivity of 1 has kind of a special name. I think there are some real materials that can get close to it, but for the most part, it's kind of a theoretical maximum. Okay? And so objects with emissivity of 1 are known as black body radiators. Okay? We'll spend a bit more time talking about black bodies. So they also have some other really nice properties with radiation as well. But for now, you can consider black bodies as having perfect emissivity. Okay, so let me pause here for a second. So are there any questions on any of this so far? Okay. Okay, and so that's the emitting side, right? And so we know that every object can emit radiation, okay? And of course, it depends on its temperature, it depends on its emissivity, but the ability to accept radiation or absorb it is also a property that's useful as well, okay? Okay. And so the ability to absorb radiation is known as irradiation. Okay. Okay. And we give that the symbol G. Okay. And so irradiation or excuse me, so the amount of irradiation that gets absorbed is known as, or is computed as alpha multiplied by regular G. Okay? Where G, this G right here is the total amount of radiation that actually hits the surface. Okay? Okay? And this G absorbed is the amount of radiation that's actually absorbed as thermal energy for that material. Okay? Okay? Because it's also possible for radiation to reflect off a surface as well. Okay. Okay. And of course, the thing that determines this is alpha. And this is another kind of coefficient quantity, just like the emissivity, but this is called the absorptivity. Okay. Okay. And so just like the emissivity, this is a coefficient, and so it's between 0 and 1. And describes, how much radiation actually gets accepted or absorbed into the material. Okay. because it's possible for an object to get hit with a lot of radiation, but for none of it to actually affect its internal energy. Okay, let's talk about a mirror, just like we talked about before. Right, so a mirror, the kind of the characteristic of a mirror is that whenever a beam of light hits it, it reflects it right back. Okay, so that's how you're able to see your reflection in the mirror. And so a mirror, you can actually shine as much radiation as you want on it. But the fascinating thing is that the mirror will actually not really heat up all that much, because most of the thermal radiation that you shine on a mirror is just gonna bounce back and come right back at you. Okay. And so in order for radiation to actually affect an object, in order for it to heat up or cool down, it has to actually absorb it. Okay. And different materials have different abilities to either absorb or reflect radiation. Okay. And so reflection is the last one that we'll talk about, although there's two more. Okay. And so there's two other things that can happen as well. So in addition to absorption, we can have reflection. Okay. And so reflection is basically the thermal radiation just kind of bounces right off the material. Okay. We won't be talking about reflection all too much, just because it's that's more optics, okay, or advanced radiation. And then we also have transmittance. Okay? So transmittance is when a radiation ray just passes right through the material without being absorbed. And so those are our four main actions you can think about in terms of radiation. So we have emission, we have absorption, we have reflection, and transmittance. Okay. So let me just go ahead and sum those up. Okay. Okay. So when we have emission, okay, so emission is when an object gives off radiation, okay, which all objects are doing all the time. Number two, we have absorption. Okay. Three, we have reflection. And four, we have transmittance or transmission. Okay. And so let me characterize these in terms of how they actually affect the thermal state of an object. Okay. And so when an object emits radiation, it's basically giving off heat. It's transferring heat from itself to its surrounding. And so when we talk about emission, what we talk about is an object losing heat. Okay. Absorption is the opposite. And so absorption is when an object takes on radiation and that changes its, and absorbs it into itself. Okay. And so when an object absorbs radiation, we say that it gains heat. Okay. Reflection and transmittance, that's when the thermal radiation basically has no effect on the object. And so these are when these have no effect really in terms of heat. Okay. Okay. And so radiation, is basically constantly happening, right? And so, every object is emitting heat, every object is absorbing heat, and that's kind of happening all the time. And so it seems like, radiation is kind of a big deal, but up until this point in the class, right now we're what, week 13? And so for 12 weeks of this semester, we've basically been ignoring radiation this whole time, okay? But it seems like there's a lot going on, right? Emission, absorption, all this stuff. And so, the question is, is it a fair assumption to ignore radiation? And luckily for us, the answer is actually yes. Okay, so for most heat transfer that occurs on planet Earth, which is most of the stuff you're going to design, usually conduction and convection are going to dominate. Okay, most of the time. And so most of the time, if you know you're going to have convection or conduction, those are usually the only ones that you have to worry about. Okay? Usually the situations where you have to worry about radiation are, one, if you don't have any material. Okay? And really, the one that kind of comes to mind the most is aerospace applications, okay? Specifically space, okay? And so if you're designing like a satellite, right, or you're designing, the Tesla that's floating around in space, and you want to, for it to absorb energy from the sun, then you have to rely on radiation and the design of the solar panels in order to make that happen. Okay. Okay, there's some Earth applications as well. Like I've actually, as part of an internship, I worked with vacuum chambers before. And so vacuum chambers, if you're not familiar with what those are, they basically, they're a chamber and they suck out all the air, all the matter. Okay. And so of course, in those situations, you have to worry about radiation. Number two, probably the most, real Earth kind of situation where you have to consider radiation is when you have extremely high temperatures. Okay. And so you're talking about things like power applications, things like high temperature forging. Okay. And the reason for this is if you go back to our formula for emissive power, okay, we have the surface temperature to the fourth power. Okay. And so fourth power is really high. And so, there's not that many formulas that you see in practice that have a fourth power like that. Okay. And so the thing with fourth power, fourth power means that you basically take itself and you multiply it by itself 4 times. Okay. And so if you have a really high number there, of course, that's going to be really significant, right? And so if you have, let's say you just have, like 270 to, about 300 Kelvin, okay? 300 Kelvin to the fourth. And so that's about room temperature. And so that's, a high number, but, still kind of manageable. But if you consider something like, 1,000 Kelvin, right? 1,000 Kelvin raised to the fourth power, that's a humongous number, right? And so, that's going to be a lot more significant than that. And so the higher temperatures that you have, the more significant radiation is, in general. Okay? And those only happen in kind of very select few applications here. All right, any questions on this before we wrap it up for today? Okay, all right, so let's call it here today. And so on Wednesday, we'll continue on with this set of lecture notes on radiation, and we'll start to do some examples. Okay? All right, so thank you everyone for coming today. Remember, homework 6 is due Wednesday, and we have midterm 2 on Monday. Okay. And so I'll see you all next time. I think there's something. Yeah. Oh, you said
Just try not to route it.
great. Yeah. These are your two convection coefficients. These are.
You got like 60 for this one. This one's relatively close to yours. Water.
You know why? It's true.
The water one.
But for this one right here, remember when you're writing by, there should be the parentheses. So it should be pi or pi times the diameter.
Got it.
Right now you do the cross section.
Okay, so when it comes to relating my work prompts to the think about problem, this right here, find the velocity. That's not DI, that's DI plus 2t because it also has emissions, right? Yes. Okay, so I just need to apply that where it counts like also the DH isn't just the outer minus the inner.
You're right, it's outer minus inner plus whatever.
So when we go to apply the DI plus 2t and not just DI, that's like the separating.
So it depends on the thickness of the, you know. Okay, and so there's sometimes we can say that, oh, we can neglect it, it's thin enough that we can neglect it. Right. I mean, in reality, you know, probably the one who's in class, where the thickness is only 1 centimeter, probably not like that, it's probably still better. Right. But if it's kind of all this, if that thickness is on the same order. So let's say your boys are like 8 centimeters, then you have.
Okay, and then when it comes to something like the H value, we don't do DI plus 2t, right? It's just DI.
Yes. So that's for the inner.
Okay, so specifically when it's dealing with like specifically just airflow, when it's like relating to the surface.
Okay. Right. Yeah. So for if you're going to do
Okay. Got it.
Okay. That makes. Yep.